Hello and welcome to Chapter 10, Section 3, Using Chords. The essential question is, what are two ways to determine when a chord is a diameter of a circle? What you will learn is how to use chords of circles to find the lengths and arc measures. So first thing we're going to start off with is a theorem. So we're going to start off with the congruent corresponding chords theorem. So if in the same circle or in congruent circles, two minor arcs are congruent if and only if the corresponding chords are congruent. All right, so what this is saying is in order for A, B here to be congruent to CD, to arc CD, in order for that to happen, I have to say that from the chord from A to B has to be the same length as the chord from C to D. All right, so in order for the arcs to be congruent, if I draw a chord between the endpoints of a chord, those two chords are going to be the same. All right, so the chords have to be the same for the arcs to also measure the same. Okay, that's our congruent corresponding chords theorem. Okay, next we have another theorem, perpendicular chord bisector theorem. So if we have a diameter of a circle that is perpendicular to a chord, then the diameter bisects the chord and its arc. All right, so what that is saying is that if I have this diameter, oh, let me do a straight line, EG, right? That's our diameter because it's a chord and it goes through the center. If that creates a perpendicular, so remember perpendicular means creates a right angle. So if our diameter creates a right angle with a chord, then that means that our chord is being divided equally. So this from F to H is the same as from D to H. So those two pieces are congruent. They're being bisected. And then my arc FG is the same as my arc GD. So that is what it's saying right here. HD, this is my two segments, so HD and HF, that's this middle, the purple. Those are the same because the diameter has a perpendicular, it creates a 90-degree angle. And that means that our arcs are also congruent. And one last theorem here before we go to our first example is the converse of that perpendicular chord bisector. So if I have one chord of a circle that is perpendicular bisector of another chord, then the first chord is the diameter. Okay, so the converse means kind of just like how it makes sense. So if I have a chord, right, this one, you can't see that it goes through the center, right? In the previous one, it clearly went through the center point, but in this one, we don't have the center point. So if I have a chord, say SQ or QS, and I notice that it creates a 90-degree angle with some other chord, then I know that QS has to be a diameter, okay? Because only the diameter can perfectly cut a chord in half. All right, so let's use congruent chords to find an arc measure. All right, so in this first one, in this diagram, okay, we know that circle P is congruent to circle Q. So these are two identical circles, all right, congruent. We know that FG is congruent to JK. So let's label those with colors. So FG there is the same as JK. And we know that the measure of our arc here, JK, is 80 degrees. So according to our first theorem, okay, this one here, congruent corresponding chords theorem, we know that if we have a chord in one circle, this here, if that chord is congruent to a chord or another chord, which it is, then we know that their arcs are also congruent to each other. So here, if we're looking for the measure of arc FG, which is this one, we know that it has to be the same as that one because their chords that connect the arcs are congruent to each other. So we know that the answer for this is 80 degrees because it has to be the same as arc JK. Okay, next we're going to have to use our other theorem. Okay, so using the diameter. Okay, so here JL is our diameter. And we see here it's creating a 90-degree angle. So we know that it is bisecting two different things in half. So we're going to use this to find HK. So what is HK? HK is from here to here. So we want that piece right there. How long is that piece? So because I know that our diameter cuts a chord in half when there's a 90-degree angle, if this is 7, then this side over here is also 7. So then HK has to be 7 plus 7, which is 14. All right, so this HK measures 14 units. All right, next up, we're looking for the measure of HK, so the arc HK. So that would be the quickest way from H to K would be this. So we want to have the measure of HK. So what we're going to do is, because the diameter is bisecting, that means that this side over here is the same as this side over here. Right? So I can set that as an equation. So I can say that 11x is the same as 70 plus x. If I solve this equation then, it's going to give me 10x is equal to 70 divided by 10, and x is equal to 7. Right? So then all I have to do is substitute. Okay, substitute. Because I need to find HK, I need to find the whole thing. So here, 11 times 7 plus the measure of this arc, which is 70 plus 7. Let's actually do that in a different color. To orange. All right, so 11x, that's going to give us the measure of JH. So 11 times 7, that's 77. And we can see that if we substitute a 7 for x, that's also going to be 77. So we want the measure of the whole arc HK, which is 77 plus 77, which is 154. All right, here we have another theorem, the equidistant chords theorem. So if in a circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So here we have a circle E. If AB, this chord here, is congruent to CD, if and only if EF, so these are the same, the two blue ones, if those two are congruent, then we know that EF is the same as EG. It has to be the same. Okay, they are the same distance away from the center. Then we have congruent chords. All right, so what we're going to do here is we're going to use all of that combined to find the value of x in this situation. And there's a lot going on here, so we're going to go ahead and take it one step at a time. So if I have in this diagram here, what it's telling me is that QR is equal to ST, right? So QR is equal to ST. Okay, and that's what it gives us right away. So because of our theorem that we just talked about, so if we have two congruent chords, then we need to know also that the two distances from the center are also the same. So for this particular question, okay, we need to know that 2x is the same as 5x minus 9. All right, so what I'm going to do is I'm going to set that as an equation so I can figure out what x is. So 2x is equal to 5x minus 9 because of the equidistant chords theorem. So what I'm going to do here then is going to solve for the equation. I'm going to move the 5x with the 2x. That's going to give me 3x, negative 3x is equal to negative 9. If I divide both sides by negative 3, x is equal to 3. All right, so that would maybe be my answer, right? That's what I would think, okay? But no, the question is asking to find the radius. So we need to take this a little step further. All right, so what we're going to do here is then figure out what is the radius. So the radius, remember, is from the center to the edge of the circle. So let's say from C to Q. Now from C to Q, we have to figure that this is a little weird because we're missing so much. There's no way we can know how that is if all we have is the 2x. So what we're going to do here is we're going to figure out some other things based on what we are given. So right here, if 2x, right, we're going to figure out what this is, what this 2x is, just to start. Okay, so 2x, because x is 3, that's going to be 2 times 3. So we have this side, this one here, is 6 units. All right, so now how does that even help us get any closer? So what we're going to have to figure out is what else do we have here? So in the question it says that QR is equal to ST, so the two blue pieces are the same. This piece and this piece are the same. And it also says that it's equal to 16. So this whole side right here, that line QR, that segment QR, is equal to 16. But if we recall, we said that the diameter bisects if we have a 90-degree angle. So because there's a 90-degree, the diameter is splitting this QR in half. So then this top part right here is 8 and this is 8. So now we have a right triangle with two sides. So I'm going to go ahead and erase all of this right here and redraw this triangle that we have so we can see exactly what I'm talking about. So I have this top side here, which measures 8. I have this left side here, this middle part, which we calculated by using the x that we found, 2 times 3. That side there is 6. And then we have this side that we don't know that measures a random, not a random, but a number we don't know yet. And we know that this is a 90-degree angle. So I have a right angle with one missing side. Let's call it x. So what I can do now is I can use the Pythagorean theorem to find the missing side. Because remember, when we have two missing sides of a right triangle, we can do a squared plus b squared is equal to c squared. 6 times 6 is 36. 8 squared, or 8 times 8, is 64. All right, we add 36 and 64. We get 100 is equal to x squared. We take the square root to both sides. The square root of 100 is 10. So actually, we should have called this different. Instead of x, because we're not looking for x, we already found x. So that's one of the mistake of the video. There's always one. We're going to change that to be an r, because that's the radius. That's a radius. So r squared, r. So r is equal to 10. So that is exactly what we're looking for. We're looking for how long is the radius. So our radius is actually 10. All right, so in this lesson, you should have learned how to find the measure of an arc using a chord. You should have learned about the perpendicular chord bisector theorem, as well as its converse, and how it can be used in sequence with the diameter to find missing measurements, and how to use congruent chords to find the missing radius. If you have any questions, comments, or concerns, please feel free to leave them in the comment section down below, and I will see you next time.